Okay, so these are some video notes from what we did today in class. Here's our example. I want to answer the question, what is the maximum height the bicycle will coast to? And I can see at the bottom, it's traveling at 10 meters per second. The mass of my bike and rider is 80 kilograms, and I'm coasting the whole time. So we're going to start off kind of simple, and I'm going to call this perfect world physics, kind of like Dr. Seuss wrote these problems. So there's no friction, there's no outside forces. All I have to deal with is something that's coasting or gliding and the force due to gravity and the energy stored in that force. So I'm not going to have any motors, rockets, brakes, or friction for these kinds of problems. So this is an example of what we'll call right now perfect world problem, and then we'll roll into the real world problems and add more energies. So to solve this problem, what I'm going to do is to compare the energies at two different locations. I'll choose my two locations carefully, one from the question, which is what is the maximum height the bicycle will coast to. That'll be the one location. And the other location, well, that's going to be somewhere on the diagram where I know the height and velocity. And that's because potential energy is mgh, so I need the height, and kinetic energy is 1 half mv squared, so I need the velocity. All right, so this is going to be the maximum height. I really don't know where it is. It's not scale, but we'll just call it that point right there. So that's what I'm looking for, is the height at that location. Location 2 is somewhere else in the diagram where I know the height and the velocity. So in this case, that'll be down here at the bottom. So as a hint, whenever a problem asks about maximum height, we're going to assume that it reaches its highest point, expends all of its kinetic energy, and comes to a rest. If you've ever coasted on a bicycle, reached the highest point on a hill, or a skateboard, or maybe in blade skates, then you know at the highest point you lose all your velocity and you come to a rest. So the other location is going to be down at the bottom where I know the speed because it tells me it's 10 meters per second, and I know the height. It's the lowest height, so I'm going to call that height 0. Whichever height is the lowest, I'm always going to call it 0, so I can change it over and over for different parts of a problem if I need to. Now at the other location, the maximum height, I've lost all my kinetic energy, so I've come to a rest. So that tells me the velocity is equal to 0 because I came to a rest at maximum height. So anytime a problem asks about maximum height, we know that's going to be true. And then I'm looking for the height, and that's the other variable that I have. Okay, let me shrink this down, make some space. So my strategy so far, I'm going to identify the fact that the problem is in our quote-unquote perfect world. In other words, I don't have any forces other than gravity. And then I'm going to identify two locations where you need the velocity and the height. Usually one of the locations will be the location indicated by the bicycle in this case, and the other one's by the question itself. So maximum height. Next steps. I need to describe to someone that I know that I'm going to use conservation of energy. So to do that, I'll use this expression. I'll do the sigma and then capital E for energy. In the method of free body diagrams, we used sigma and we used F, capital F, for the forces, but now we're using sigma, capital E, and then a subscript describing the location. So in this case, it's the bottom, and on the right-hand side, you can see I have maximum height. Be expressive. Don't be too short in what you're doing. Abbreviate it because you're only going to write it once, so take a couple seconds and do it right. Next step, I'll write down the energies that I know I'm looking for, and I'll just write them down, not with equations, but with expressions. So Ke for kinetic energy, Pe for potential energy, and in this case, it's potential energy due to gravity. So those are the only energies right now that I'm considering in my perfect world scenario. And then I'll begin to eliminate energies and plugging in numbers. So let's talk about how I do that. I'm going to start with the LOL diagrams that we did in our introductory activity. And I've got one for the one location, that's the maximum height, and I've got another for the other location, that's the bottom of the hill. At the maximum height, I know I have a total amount of energy. And when I reach the maximum height, that's defined as maximum height when the velocity is equal to 0. That means there's no motion, so there's no kinetic energy. So all my energy at the top at maximum height is in potential energy. At the bottom of the hill, it's total energy. And at the bottom of the hill, well, it's the lower of the two heights, and it's got all the velocity. So because it has all the velocity there, it's got kinetic energy, and because it's the lowest of the two heights, it doesn't have any potential energy. So this LOL diagram for the energies tells me that on one side of the equation I'm only going to have mgh, on the other side I'm going to have 1 fmv squared, because that's where the red bars are. One's at the potential energy and one's at the kinetic energy. So now, let's look at it another way. The first thing I'm doing is writing my summation for conservation of energy. I do that no matter what method I choose. The next thing I'm going to do is look at what energies I'm considering. So right now it's just Ke and Pe. That's easy. And now I need to figure out which of these go to 0. So I can see on my diagram that on the hill bottom, PE is going to go to 0, and on my diagram down below, the kinetic energy is going to go to 0. But there's another way to think about this. I can also ask some simple questions. So I can ask, is it moving at this location? Is it above the other location? So in other words, at the bottom of the hill, is it moving at that location? The answer is yes. It's moving at 10 meters per second. So I'm going to keep KE in my equation. Then I'll ask my other question here, is it above the other location? Actually, it's not above the other location. So I'll put just a diagonal line through it to say I'm not going to consider it. And it means at the bottom it's only kinetic energy, which is what we saw in the LOL energy diagrams. Next, I'll look at the maximum height. At the maximum height, is it moving? No. That's what maximum height is defined as. So I've lost all my kinetic energy, and all I have is PE. So now I can finish this up, and I'll use my equations. KE is 1F mv squared, PE is mgh. Same thing I would have gotten from those LOL diagrams, just another way of thinking about it. Now, another cool thing about this setup is right now, this perfect world setup we have, the masses are in every expression, so they will divide out. Doesn't always happen, but it does here. So now 1/2 v squared is equal to gh. Time to plug and check our numbers and figure out what the answer is. So first thing I'll do here is isolate h. H is equal to v squared divided by 2g, dividing both sides by g. And that's 10 meters per second squared, 10 meters per second quantity squared, divided by 2 times 9.8 meters per second squared. And that'll give me the height. When I do the math, I get 5.10 meters. Make sure when you're plugging in numbers, we still plug in numbers and units. So, as a recap, when I'm given the problem, I need to set up and compare two energies. So I'll pick one location based upon the question. The second location is somewhere else where I know my energies, in this case, velocity and height. Then I'll write my expression, sigma energy at one location equals sigma energy at the other location. I'll write KE plus PE equals KE plus PE. I'll use whichever method I'm comfortable with, getting rid of an energy to make my equation shorter. Then I'll use my expressions with the regular equations for kinetic energy and the potential energy. In this case, I can simplify and I isolate the unknown, put in my numbers and units, and do my math. Then I get the 5.10 meters.